Good morning, class. We are looking at section 5.4, the substitution rule, and the session is being recorded. We are looking at integration formulas. As always, we should be very comfortable with them to be able to move on. I'm hoping we are okay with those. What I want to quickly recap is the constant. You have a dx here, therefore kx plus c, the power rule. You divide by n plus 1 to the power of n plus 1 on a constant. These two refer to the fact that you do them term by term, and if there is a constant multiple, you keep it. X to the power of -1 is the same as 1 over x, and therefore the answer is natural log. For exponential, you divide by k. The derivative of sine is cosine, but the integral of that is negative cosine. The derivative of cosine is negative sine, and its integral is positive sine. The fundamental theorem of calculus, the derivative of the integration gives you the function back. They undo each other. And of course, this definite integral, the integral of a to b f of x dx, is capital F of b minus f of a. We do have a more trigonometric functions here. The derivative of tangent is secant squared, so the integral of secant squared is tan x. The derivative of cotangent is negative cosecant squared, so the integral of cosecant squared is minus cotangent x. The derivative of secant is secant tan, so the integral of secant tan is secant x. The derivative of cosecant is cosecant cotangent, so negative cosecant cotangent, and the integral of cosecant cotangent is negative cosecant x. All of them, you have to add a constant. Now, what is substitution? First, let's take a look at differentiation. What are we differentiating? We are differentiating using the chain rule because substitution is the reverse process of that. The derivative of capital F of g of x is capital F prime of g of x times g prime of x, or if we represent capital F prime with lowercase f, we can say lowercase f g of x times g prime. So if we let g of x be represented by a function u, then du is g prime of x dx. In other words, if u is g of x, then we can say du dx is g prime of x, and therefore du is g prime of x times dx. So we can go back as the derivative of this results in this, the integral of that results in the original function. So that's the substitution method. To write it officially, we say over any interval for which u equals g of x is a continuously differentiable and f is continuous on the range of this function, the following is true. Lowercase f g of x times g prime of x dx, where g of x is represented by u, g prime is du dx, and g prime times dx is du. The result will be capital F of u plus a constant, or and we replace the u back, or capital F of g of x plus a constant. Let's make some sense out of this by looking at a few examples. First and foremost, we're going to look at a couple of polynomials. When we have polynomials involved, normally the more complicated function is the choice of u. So the tip is look for a function u equals g of x anywhere here and look for its derivative, du, or g prime of x multiplied by dx. Normally, the more complicated function, as I mentioned, is the choice of u. I hope you realize we have a parenthesis to the power of 3, and the parentheses and what's inside is more complicated than what's outside. And it's a trial and error. You can check it out, see if it works out or not. So if we choose the inside of the parentheses, namely x squared plus 5 bu, I hope you realize the derivative is 2x, therefore du is 2x dx. If you will, I can write from here du dx is 2x, and therefore du is 2x times dx. Again, just in the beginning, if you want to write that, you don't have to, if you know what du means. So it's a good practice that move the 2x next to dx. So you see the combination is du. Take a look. This is u to the third power. When you move the 2x next to dx, the whole thing becomes du. And therefore, we are dealing with the simple case of a power rule. So I hope you see the transition. That's the most important thing. Now this gives you 1/4 u to the power of 4 plus a constant. We replace the u with the choice of u, which was x squared plus 5, and we are done. In the beginning, it's a good practice to differentiate the result. It must give you the same answer without the dx. So you can differentiate this. It should give you the integrand without the dx. You can practice that in the beginning. Here's a similar example. Remember, normally the more complicated polynomial function is a choice of u. I hope you realize the parentheses is the more complicated one. So you're looking for that. So if we choose this one to be u, its derivative is 3x squared. So du is 3x squared times dx, and we have it there. So note that 3x squared is the derivative of that. Therefore, we go with the following. (3x squared, x cubed plus 1 to the power of 10 dx). We move things around. Again, you don't have to do that, but it's really a good practice. So it becomes clear. This in combination with dx, the whole thing is du. So let's write this. U is the parentheses and what's inside. Du is 3x squared dx, and therefore the original integration becomes a simple case of a power. Whether you want to take too many steps to go there, or simply from here write this one and write this one. So I would go from here to here and here. In the beginning, put the 3x squared next to dx. That is really helpful until you get very comfortable with that. So the answer is 1/11, u to the power of 11 on a constant. And finally, replace the u with x cubed plus 1. And that's the final answer. By the way, I'm sure everybody knows whether I put 1/11 u to the power of 11 or u to the power of 11/11 makes no difference. Same thing here. Of course, we can multiply it. We can distribute and do the work without the substitution. But the purpose of this question is to use the substitution. And I hope you see this is the more complicated one. And its derivative is 2x plus 3. So if you choose the first parentheses as u, this is times dx equal to du. So what happens to 9? 9, you keep it inside or outside. The integration sign makes no difference. It is a multiplier. Therefore, we have the new integral of 9u du. Power rule. 9/2 u squared and a constant, where u is x squared plus 3x plus 5. And we are done. Again, in the beginning, if you have any doubts, we want to differentiate the result. It should give us back this whole thing without the dx. Okay? It will give us the integrand without the dx. So that's the case with polynomials. I want to switch gears and look at different types of functions. Anytime we are dealing with a fractional expression or a rational expression, the first step is, can I simplify? Can I factor anything? Can I divide the top by the bottom? That is our first step. If we cannot, then we move on to the second part. The second part being, okay, what is my choice of u? What is du? In that case, most of the time, the denominator is a choice of u. So notice, if you let u be the denominator, which is 5 plus e to the power of t, then the numerator is the derivative of that. So du dt is e to the power of t, and therefore du is e to the power of t dt. Notice dt is really, in essence, you can write it in the numerator. So here's what we are going to do. Let u be 5 plus e to the power of t. Therefore, du is e to the power of t dt. I'm going to put the dt at top so it becomes clear they are sitting next to each other. And therefore, we have du over u, or one over u du, however you want to write that. The point being, you have to recognize this is natural law. Replace the u, and we're done. If in this case you don't write the absolute value, that's fine. The reason being, because 5 plus e to the power of t is always positive. That's why if you didn't use the absolute value, it's fine. If you're not too sure, you must use it. Although part A has got nothing to do with part B, but I put them next to each other so you can see the similarities. This is a fractional expression. This is a rational expression. We're going to treat them the same. Can I simplify? The answer is no. Why not? Because the denominator can't be factored. I hope you remember when I went over this concept that one easy way to see whether you can factor or not is to calculate b squared minus 4ac. If it's a perfect square, it can be factored. In the denominator, b is 2 squared, minus 4. A is the coefficient of x squared, which is 1. C is the constant, which is -1. They add up to 8. 8 is not a perfect square. Therefore, it can't be factored. So what do? We basically try to mimic part A. If the denominator is a choice of u, so what is the derivative of this? Is 2x plus 2, or 2 times x plus 1. So if this is u, du is 2 times x plus 1 dx. Notice I can put this in a parenthesis dx next to it, and I compare it to du. They're almost the same with the exception of number 2 missing there. Now, What the text does, and many texts, they do it in the same manner, is that they solve for dx. I'm not going to go that route. I'm going to show you an easier way. The easier way is anytime a number is missing, you can multiply and divide by it as follows. Take a look. So the numerator class is x plus 1 times dx, and number 2 is missing. So I'm going to multiply by 2, and I'm going to divide by 2 by writing its reciprocal. Please understand the product of these two is 1, and we can only do that if a number is involved, not a variable. Because a number is involved, I'm going to do that. So the numerator becomes du, the denominator is u, and the 1/2 doesn't go away. So let's quickly recap. If we choose u to be the denominator, the numerator has a missing factor of 2 to become du. Because 2 is a multiplier, is a number you can multiply and divide by. Now this is also a natural log. So we have a 1/2 in front of it. And the u must be replaced with x squared plus 2x minus 1. Here's the final answer. You have to keep the absolute value because this expression x squared plus 2x minus 1 can be positive, can be negative, and therefore we must keep the absolute. Now, for the sake of comparing and contrasting, I'm going to give you this question to see how we handle that. And I want you to look at that, compare it to A. It's the reciprocal of that. In the case of part A, we had to go with the substitution because there was nothing we could do. But as I mentioned, anytime you have a fractional expression or a rational expression, see if you can make a division, see if you can make it simpler. And in this case, if I cut it into 2 fractions, the first one becomes 5 e to the power of negative t, and the second one becomes 1. I don't need a substitution. I divide by negative 1 becomes minus 5 e to the power of negative t plus 1. Because it's dt, 1 gives me t and a constant, and we are done. This would be a good page that you look at all of these 3 questions simultaneously, compare and contrast, and become comfortable with rational expressions, fractional expressions, and know where to use and when to use the substitution method. In this course, and in most cases, anytime E is involved, the choice of u normally is its exponent. So take a look at what happens with part A. If we choose the exponent x to the power of 5 to be u, the derivative of that is 5x to the power of 4. Therefore, du is 5x to the power of 4 dx. So the choice of u is the exponent. Now, let's move this next to dx so we can clearly see we have e to the power of u du. Again, you don't have to do that, but it's a good practice, at least in the beginning. This is the same as the original one. Now we can clearly see this is e to the power of u, and this whole thing is du. The answer is itself e to the power of u and a constant. Now you replace the u, and you're done. If you have any doubts, you can differentiate this. I hope you realize quickly if you differentiate this, you get the same thing times the derivative of this, which is 5x to the power of 4. So it gives you this answer, and you're fine. For part B, we do exactly the same. The choice of u is the exponent, which is x to the power of 5 minus 2, and the derivative of that is 5x to the power of 4. So du is 5x to the power of 4 dx. Notice I put number 5 in a different color because when I move this next to dx, number 5 is missing. And I'm showing you the easy way out. When number 5 is missing, the way I approach it is that, okay, I put number 5 and I undo it by multiplication by its reciprocal. You can do that to only numbers, not variables, class. So again, I need number 5, I multiply by 5, I divide by 5. Therefore, it's 1/5. The first piece is e to the power of u, and the second piece is du. This again gives you e to the power of u and a constant. Never mind the 1/5, it remains, and replace the u. And you're done. So in the case of a exponential, as you can see, the choice of u is normally the exponent, and it works. Now, I've chosen this question because I want to do it by the method that the text and most texts do, which means we need to use the substitution, and u equals 3x plus 7, du is 3 dx, and they solve for dx. The way I would do that, remember, number 3 is missing. I would throw in number 3 and 1/3 out. But the way they do it, they solve for dx. And this is an extremely simple problem that really doesn't make that much of a difference. But the more complicated this expression, the more difficult this method. I want you to know that. So solve for dx. And therefore, they are going to replace this with u and dx with du over 3. Needless to say, square root of u, that means u to the power of 1/2. And this is du over 3, or 1/3 of u. What would I do? Over here, I need number 3, so I throw in number 3, and I throw out 1/3 outside the integral sign. This is the way I would approach it. And notice, that gives you exactly the same thing. Okay, this 1/3 is there. That it gives you exactly the same thing. Square root of u du. This one is square root of u du. We are going to differentiate, so 1/3 remains, number 1/3 remains. Now u to the power of 1/2 differentiation will give us this. Why is that? Because 1 over 1/2 plus 1, u to the power of 1/2 plus 1. We've done this many times before. 1/2 plus 1 is 3/2, so reciprocal of that is 2/3. This is what we get now, 2 over 9, u to the power of 3/2, and u is replaced by 3x plus 7. So I wanted you to be exposed to this method. You've seen it. I would take the easy way out. Again, I have a couple of questions next to each other because ultimately they use the same methodology, namely when ln x is involved, and at least for this course, that is the choice of u for us, okay, class? So in both cases, we see ln x. So if we choose u to be ln x, du is 1 over x dx. Now, let's rewrite the first one so we can clearly see different components. Take a look. We're going to write ln x to the second power, then 1 over x dx, we put them next to each other. Therefore, this is u squared, and this whole thing is du. And now we also have a power rule here. 1/3 u cubed plus a constant. U is replaced by ln x. We are done here. However, I want to make sure that we understand that ln x being raised to the third power is not the same as ln of x cubed. They are not the same. This can be simplified to 3 ln x, not the other one, because it's only x that is being raised to the power. It's ln of x cubed, whereas the other one is ln x times ln x times ln x. Part B, we use the same substitution. And let's rewrite this as 1 over ln x times dx over x. By the way, I hope you realize that 1 over x dx or dx over x, these two are the same. And on purpose, I wrote it differently because I want you to be exposed to both. In case you see this one or this one, they both mean the same thing. So 1 over ln x, that means 1 over u, and this one is du. By the way, you could write this as du over u or just 1 over u du. Again, both of them mean the same thing. You want to, let me just write that. This is the same as saying the integral of du over u. And the result is a natural log. So the natural log of u and a constant, where u itself is ln x. So ln of ln x, ln of ln x plus a constant. That's the final answer. Again, I have a couple of questions next to each other because we want to compare and contrast. Anytime you're dealing with sinusoidal functions, if the argument has a power, normally that is the choice of u. So if you choose u to be x squared, its derivative is 2x dx. And so what happens if you put the x next to dx, everything is there except 2. Remember, a number is missing, we can multiply by it and divide by it. So we put the x next to dx, we throw in number 2, that means we are multiplying by it. To undo that, we multiply by its reciprocal 1/2, or we divide by it, 2. Therefore, you're looking at 1/2 sine u du. The derivative of sine is cosine. The integral of sine is negative cosine. And u is replaced with x squared. You can always differentiate the final result, and it gives you the same answer. What is the difference between A and B? Part A, the argument is being raised to a power. Part B, either sine or cosine. It doesn't matter which one, class, because the derivative of sine is cosine and the derivative of cosine is negative sine. The one that is being raised to the power is a choice of you. So if you choose sine, by the way, I want to make sure that everybody understands this means sine x to the second power. Therefore, if you choose u to be sine x, du becomes cosine x dx. We rewrite this as the integral of u squared du, which is clearly a case of a power rule, 1/3 u cubed plus a constant. replace the u with sine, so 1/3 sine cubed x. Pay attention to the location of this. This is atop of sine, not x. In other words, this is the same as sine x to the third. They are both the same. Now, what happens when we want to evaluate a definite integral of a to b? A to b f of x dx when substitution is in order. So the substitution for this is simple. We've seen this before. But I want to show you two methods. Again, you're dealing with polynomials. The more complicated one is x squared minus 1, right? You remember that? So that's the choice of u. And dx and du is 2x dx. So let's write that. U is the more complicated one, du is 2x dx. So if you put the 2x next to dx, you have your du. Notice what I'm going to do. I'm not going to write the limits 1 and 2 because 1 and 2 pertain to x and not to u. Therefore, I'm going to put a question mark, meaning I don't know. And at this point, I don't care. You get u cubed. Du, the integral of that is 1/4 u to the power of 4. I don't have a limit. So I'm going to go back to the original u, which is x squared minus 1, original variable x. And now I'm going to put the original limits. I put number 2, 2 squared is 4, minus 1 is 3. 3 to the power of 4 becomes 81. If I put 1, it becomes 0. So 1/4, 81 minus 0, this is the answer, you're done. So you can always go back to the original variable and you're done, there's nothing wrong with that. However, in many cases, it's easier to actually use the new variable and therefore new limits. The limits almost always change as follows. All you have to do, look at u and plug in the lower limit. If I plug in 1, I get 0. That means the old lower limit 1 results in new limit, lower limit 0. So this is 0. If I put the old upper limit 2, 2 squared minus 1 is 3. So the new one is 3. So take a look. Keep track of the change of variables in the limits of integration as follows. So x is 1, the lower limit, put it into the u, and you get 0. X is 2, the upper limit, put it into the u, and you have the new upper limit. So you write this one with the old limits is the same as this one with the new limits 0 and 3. And therefore, this is 1/4 u to the power of 4 from 0 to 3. And obviously, if you plug in 3, you get 3 to the power of 4, which is 81 over 4. And if you plug in 0, you get 0. And I think this is a tad easier to evaluate than this one, but makes no difference. Both of them give us the same answer. Therefore, if g prime of x is a continuous function on a comma b and f is continuous on the range of u equals g of x, then the integral of a to b f of g of x g prime of x dx is the integral of g of a to g of b f of u du. In other words, if you change this with a u substitution, remember u is the same as g of x class. This is a, this is b. Therefore, you plug in a and b into g of x to find the new limits.